How computers display raw, low-level text and graphics. My ever-growing interest in computers is making me ask deeper questions, that we don't seem to have to ask anymore. Our computers, at boot, as far as I understand it, are in text mode, in which a character can be displayed using the software interrupts 0x10 when A equals 0x0e. We've all seen the famous booting font that always looks the same, regardless of what computer is booting. So, how on earth do computers output graphics at the lowest level, say, below the OS? And also, surely graphics aren't outputted a pixel at a time using software interrupts, as that sounds very slow. Is there a standard that defines basic outputting of vertices, polygons, fonts, etc. below OpenGL, for example, which OpenGL might use? What makes me ask is why OS can often be fine without official drivers installed. How do they do that? Apologies if my assumptions are incorrect. I would be very grateful for elaboration on these topics.
That's, partly, the role of the BIOS. The basic input-output system of the computer is responsible for providing a common interface to operating systems, despite such differences between actual computers. That said, for graphics specifically, there are different ways of drawing to the screen. There are T commands that you can send to the BIOS, but that's only in real mode. If you want to draw anything in protected mode, you need to use VGA to draw things. I can't explain it better than OSDev, so look here for more info, but basically, you can write to memory. Video memory is memory mapped, starting at address 0xb8000 to draw things on the screen. If you need higher resolution than VGA, you need to use the VISA BIOS extensions. I'm not familiar with it, but try looking at the Grub source code for more info. Some useful references. Grub source code. OSDev Wiki, drawing in protected mode. VISA BIOS extensions. If you happen to be familiar with D, I wrote a little bootloader a while back that was able to write to the screen, text only. If you're interested, here's the code.
From the early days of the IBM PC and its clones, the display adapter hardware was very simple. A small block of memory was dedicated to a grid of character cells, 80 by 25 characters in the standard mode, with 2 bytes of memory for each cell. 1 byte selected the character, and the other selected its attributes, foreground and background colors plus blink control for color adapters, bold, underlined, blinking, or reverse video for monochrome adapters. The video output hardware looked up pixels from a ROM table of character shapes according to the contents of character memory. In order to offer a certain degree of hardware independence, the BIOS interface to the character map required a software interrupt to be executed in order to set a single character cell on the screen. This was slow and inefficient. However, The character memory was directly addressable by the CPU as well, so if you knew what hardware was present, you could write directly to memory instead. Either way, once set, the character would remain on screen until changed, and the total character memory you needed to work with was 4000 bytes, about the size of a single 32 by 32 full-color texture today. In the graphics modes, the situation was similar. Each pixel on screen is associated with a particular location in memory, and there was a BIOS set pixel interface, but high-performance work required writing directly to memory. Later standards like VESA let the system do a few slow BIOS-based queries to learn the memory layout of the hardware, then work directly with memory. This is how an OS can display graphics without a specialized driver, although modern OSes do also include basic drivers for every major GPU manufacturer's hardware. Even the newest NVIDIA card will support several different backwards compatibility modes, probably all the way back to IBM Kira. One important difference between 3D graphics and 2D is that in 2D you don't generally need to redraw the entire screen every frame. In 3D, if the camera moves even a tiny bit, every pixel on the screen might change. In 2D, if you aren't scrolling, most of the screen will be unchanged frame to frame, and even if you are scrolling, you can generally do a fast memory-to-memory copy instead of recomposing the whole scene. So it's nothing like having to execute in 10 hours for every pixel every frame. Source: I'm really old.
During boot, the system BIOS looks for the video adapter. In particular, it looks for the video adapter's built-in BIOS program and runs it. This BIOS is normally found at location C000H in memory. The system BIOS executes the video BIOS, which initializes the video adapter. Which levels or modes of video/graphics the BIOS can display natively, without an OS or drivers, is primarily dependent on the video BIOS itself. Source/more info here, system boot sequence.
Our computers, at boot, as far as I understand it, are in text mode, in which a character can be displayed using the software interrupt 0 by 10 when A equals 0 by 0E. You're talking about legacy BIOS functions. In fact, you don't need to use such functions at all. You directly write them into video memory. How on earth do computers output graphics at the lowest level, say, below the OS? This strongly has to do on how the OS operates. Anyway, the operation is the same at the hardware level. Video card has a video RAM, which stores, simplifying, the next image to be drawn on the screen. You can think that each address is a byte which represents a pixel. Actually, generally you need more than 1 byte per pixel. Then the video controller takes care of translating this into a signal the monitor understands. Is there a standard that defines basic outputting of vertices, polygons, fonts, etc. below OpenGL, for example, which OpenGL might use? As far as I know, no. There are no standards about logical graphic representations. What makes me ask is why OS can often be fine without official drivers installed. How do they do that? Because it has drivers already bundled with the OS.
If you want to support the channel, please consider subscribing.